Hi, my name is Colin, and I'm presenting our work, Joint Forecasting of Panoptic Segmentations with Difference Attention. This work focuses on the task of panoptic segmentation forecasting. Given a series of T RGB images, the task is to anticipate the panoptic segmentation that corresponds to an unobserved feature frame. Last year, we introduced one of the first panoptic segmentation forecasting approaches. At a high level, this approach splits the scene into foreground and background and uses separate models to predict both. A simple stacking-based aggregation is used to combine these predictions. Finally, future camera motion is forecasted using an RNN-based model. The first approach has a few inherent limitations. First, each foreground instance is processed separately by an RNN-based model, which can lead to unnatural, misaligned predictions. Second, the use of simple stacking assumes that foreground instances are always located on top of background objects. To fix these problems, we reuse the overall framework, but we modify two components. First, we are going to replace the RNN-based instance forecasting model with a transformer-based approach, which allows for joint modeling of the instances. This model is inspired by the agent-former model introduced in ICCV 2021, but it is modified to forecast instance masks. Here's an overview. We represent predictions using bounding boxes and appearance features obtained from maskRCNN. These are input into two transformer encoders, which encode instance motion and appearance respectively. The produced embeddings are input into two transformer decoders to autoregressively predict future instance appearance and location. Notably, the appearance transformers use convolutional layers in place of all linear projections to maintain spatial feature information, and the location transformers use a new attention module titled Difference Attention, which is designed to naturally encode quantities such as velocity and acceleration. Let's describe difference attention in more detail. Attention layers process two input feature tensors, where the first set of features is updated as a function of the second. For standard attention, we compute queries, keys, and values. We then compute attention scores from the key and query, and then use these to aggregate values, producing the final output. For difference attention, we follow the same structure. However, both attention score computation and value aggregation are now a function of differences between our inputs. Doing this allows the model to more naturally encode and reason about quantities which are represented by differences, such as velocity and acceleration. Our second advancement is to replace simple aggregation with a prediction refinement head. At a high level, the prediction refinement head determines which prediction, either instance or background, to output at every pixel based on the corresponding depths. The previous framework only provides us with incomplete and noisy background depths, so we must first complete these. We do this in two steps. First, we fill in the holes in the input background depths. Next, we add an offset. These are predicted from the background depth and semantic inputs using a small convolutional network. The second step of refinement is to select between the instances and background. We stack all of our depth inputs, and additionally, we compute a value matrix as a function of the background and foreground logits. Then, we obtain object selection scores using these depths and values. These are used to select the appropriate foreground or background slice at every pixel, which is then used to produce the final prediction. To evaluate these developments, we use two datasets. The first is the standard Cityscapes dataset. Cityscapes does not have sequence labels, so we evaluate using the standard panoptic quality metric. The second dataset is the synthetically generated AIO drive dataset. Note that this dataset is annotated using only two things classes. AIO drive has labels for every frame, including object tracks. Hence, we additionally evaluate using a new metric titled PQID. This is computed the same way as PQ, but it additionally requires instance predictions to have a correct instance ID. Here are the metrics on Cityscapes. This model is state-of-the-art on all metrics for the forecasting task. The biggest improvement comes from things PQ, which is over 2 points higher in both cases. Here are some visual comparisons between the approaches. Note that our model properly places instances behind background objects such as poles and signs, which can be observed in the first two columns. Second, the interaction modeling means our approach makes fewer mistakes due to incoherent output. See the cyclist and the bike in the right column. Here are the results on the AIO drive dataset. We use two primary settings here. The first uses depths obtained from stereo image inputs. The second uses ground truth depths. In both cases, our model outperforms the others on things PQ and PQID. Here are some visualizations on AIO drive. Once again, we can see that our approach better reasons about the interactions among instances, leading to more consistent outputs. Thanks for watching. We have more details and further experimental results, including ablations and more visualizations in the full paper. Code can be found at the provided link.